You pull out your phone, open a map app, and instantly see that little blue dot showing exactly where you are on the street. We all do it, right? Dozens of times a day without a second thought. But behind that seemingly simple blue dot is a massive, real-time 3D geometry problem. It's playing out constantly between the device in your hand and a network of satellites hurtling through space. And honestly, the wildest part? Your phone and those satellites don't even speak the same spatial language. Transforming between their different reference frames isn't just some minor background technical detail, it is the absolute foundation of how global navigation satellite systems, or GNSS, actually work. So let's dive into this explainer and decode the invisible math of navigation. Here's our quick roadmap for today. We'll start with the 3D geometry problem, move out to the satellite view known as ECEF, come back down to the human view called geodetic, zoom right into the local view, or ENU, and finally look at why local frames matter so much. Let's get right into it. Section 1. The 3D geometry problem, lost in translation. To really grasp GNSS positioning, we first have to understand the core conflict happening miles above our heads. We've got satellites orbiting the Earth, human beings walking around on the surface, and a whole lot of atmospheric interference trapped in between. Which brings us to a huge pivotal question. How exactly does raw space math become your actual street address? I mean, think about the sheer gap in perspective here. A satellite is flying thousands of miles above the planet, operating on a vast planetary scale. You, on the other hand, you just want to know if you should turn left or right at the next traffic light. Bridging that massive gap requires an incredible feat of continuous, real-time mathematical translation. GNSS positioning is, at its core, a geometry problem in 3D space. But here's the catch. Because satellites operate in a global frame, humans think in latitude and longitude, and signal errors happen in our immediate physical surroundings, well, we end up with a total clash of frameworks. The crucial point here is that transforming between these different reference frames is not optional, it's not a nice to have, it is structural to the interpretation of the data. Without these translations happening instantly, the satellite signals are literally useless to us. Let's do a quick breakdown of the three mathematical frameworks that make all of this possible. First, we have ECES, which originates right at the Earth's center and is primarily used for satellite computations. Second, there's geodetic, which maps the Earth's curved surface. That's the one we humans use to navigate. And third, we have ENU, which originates exactly at your local receiver and is primarily used for analyzing real-world errors. We're going to unpack each of these step by step. Section 2. The satellite view, ECEF, the language of computation. So, to figure out where we are, we have to start by looking at the Earth from the outside in, speaking the raw mathematical language of computation. Satellites naturally express their location in a global frame called ECEF, which stands for Earth-Centered Earth-Fixed. Imagine a giant 3D Cartesian grid, with X, Y, and Z axes, where the dead center origin point is the exact center of the Earth's mass. This grid is fixed to the Earth, meaning it rotates right along with the planet. This is the raw mathematical language satellites use. It's perfectly designed for calculating satellite ephemeris, which is just a fancy technical term for tracking exactly where the satellite is in the sky, as well as predicting orbit propagation and building measurement models. It's incredibly precise. But to a person standing on the street, an ECF coordinate means absolutely nothing. Section 3. The human view. Geodetic, translating for humans. Now we have to translate those massive celestial coordinates into something you and I can actually understand. I don't know about you, but I don't walk around thinking, yes, I'm currently at X coordinate 4 million, Y coordinate 2 million. No, we think in latitude, longitude, and height. This is known as the geodetic frame. Transforming ECEF into geodetic coordinates is how we map a satellite's spatial data to human logic. But this isn't just a simple one-to-one swap. It requires a highly complex, non-linear translation. And the reason for that complexity? It's actually pretty fascinating. We're all basically taught that the Earth is a sphere, right? Well, for casual mapping, sure, a sphere works fine. But for GNSS, that is a fundamentally flawed model. The Earth's rotation actually creates an equatorial bulge, meaning our planet is shaped more like a slightly squished ellipsoid. To do the math correctly, GNSS systems have to model the Earth using very specific parameters: a semi-major axis, denoted mathematically as A, and a flattening factor, denoted as F, like the ones used in the World Geodetic System 1984. As our source material points out, this directly affects height definition, mapping between ECF and geodetic, and accuracy at the centimeter to meter level. Basically, if we didn't account for the fact that the Earth is a squished ellipsoid, that blue dot on your phone wouldn't be accurate to the centimeter. It could be wildly off. Recognizing the specific, slightly wonky geometric shape is the secret sauce that makes high-accuracy navigation possible in the first place. Section 4, the local view, ENU, the tangent plane. Okay, so we've got the global space view and the curved human view. Now let's zoom all the way down to the exact patch of ground where your feet are standing. This local frame is called ENU, which stands for east, north, up. While the geodetic frame deals with the curved surface of the Earth, ENU creates a flat local tangent plane directly at your receiver. Think of it like balancing a perfectly flat, rigid geometric board on top of a curved globe, right at the exact spot you are standing. It serves as a linear approximation of the Earth's surface for your specific area. Getting from the global center of the Earth to this flat, local plane is purely a rotation problem, handled through mathematical matrices. It's kind of a two-step dance. Step 1 involves rotating about the z-axis using your longitude. Step 2 requires tilting that frame to match your local tangent plane using your latitude. Physically, you are taking the global geometry of the entire universe and completely reorienting it so that it's anchored to your exact localized viewpoint. Once we're successfully anchored in this flat ENU frame, we unlock some incredibly vital capabilities. From here, we can actually calculate a satellite's elevation and azimuth. Elevation helps us figure out visibility masking. That's basically the system asking, is this satellite so low on the horizon that a skyscraper is probably blocking it? Azimuth helps us weight measurements based on where satellites are clustered in the sky, which prevents errors in calculating your position. Ultimately, translating down to this local level is the absolute prerequisite for modeling all navigation errors. Section 5. Why local frames matter, making sense of errors. Ultimately, local frames are all about making sense of real-world interference, because out in the real world, signals get messy. Global coordinates don't intuitively tell us why a GPS signal is bouncing off a glass building. In the local frame, however, we can see clearly that vertical error, the up direction, is consistently much worse than horizontal error. We can see that multipath interference, where signals echo and bounce off objects, mostly affects satellites sitting at a low elevation. Plus, the troposphere, our active weather layer, causes signal delays that map very strongly into that up direction. All these GNSS errors only behave intuitively when we look at them in this localized east-north-up reality. If you take away just one thing from this explainer today, it should be this simple but profound distinction. ECF is for computation. ENU is for understanding. We completely rely on that vast Earth-centered frame to let the computers do the heavy mathematical lifting, but we utterly depend on the localized, flat plane frame to make sense of the chaotic, physical world we actually live and navigate in. All of this leaves us with something incredibly interesting to think about. The next time you're trying to find a restaurant and your phone temporarily places you inside a river or on the wrong city block, ask yourself, if your receiver gets your location wrong, was it a failure of computation or a failure of translation? Was the math actually wrong, or did a skyscraper or a weird weather pattern disrupt the delicate structural translation happening silently in your pocket? It's a pretty great reminder of the invisible, deeply complex spatial geometry that guides our modern lives every single day.